All right, this week we are going to use the trig ratios that we learned last week to solve for missing side lengths on right triangles. So this example says to write a trig ratio for each given angle with the given side lengths. Then use it to find the length of the indicated side and round to the nearest tenth. So before we start, just a reminder that the nearest tenth means you're going to be using one number after the decimal place. Okay, so to figure out which trig ratio I'm going to use, I'm going to label the sides of my triangle like we were doing last week. So we're starting from this 65-degree angle. The opposite side is the one that's diagonally across from it, so the side that has this B on it over here. And last week we talked about the hypotenuse was the longest side. We can't always tell because not all the sides have numbers on them. Another way to think about it is the hypotenuse is always across from the right angle. So in this case, my hypotenuse is 17 centimeters, which means this side over here is the adjacent. Now to figure out which trig ratio to use, I'm going to think back to SOHCAHTOA, and I like to write this on my paper all the time so that I don't forget it. So SOHCAHTOA reminds us that the sine is the opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. So in this case, my opposite side is what I'm trying to figure out. The hypotenuse we know, and we don't have any information about that adjacent side, so we're not going to use the adjacent side. So I'm trying to see which trig ratio uses the opposite and the hypotenuse. That's going to be sine. So when I set this up, like I said, we're using sine, and then the measure of the angle goes with sine. So the sine of 65 is equal to my opposite side, which they've labeled as B, over the hypotenuse, which is 17 centimeters. So there we go. We set up our trig ratio, and now we just need to solve for that missing side length. So right now, B is being divided by 17. The opposite of division is multiplication. So to undo that division, I'm going to multiply both sides of the equation by 17. So on the left-hand side, we get 17 times the sine of 65 equals B. So now we've gotten B by itself, but I don't know what the sine, 17 times the sine of 65 is equal to. The sine of 65 is just a number, and to figure out what that number is, if you have your own graphing calculator, you can do it in your graphing calculator, or if you go to desmos.com, it'll take you to this website here, and it's a free graphing calculator for you to use. We're going to click right here where it says scientific. And this scientific calculator has buttons for the sine, cosine, and tangent. So we're trying to figure out 17 times the sine of 65. Just type all that in, and it's telling me that the 17 times the sine of 65 is about 15.4. So if I go back to my problem, 17 times the sine of 65 is the same thing as 15.4. In this case, our triangle, the side lengths are in centimeters, so I'm going to include centimeters. And that's our missing side length. That's all we have to do. I'm going to do 2 more examples, so follow along if you would like. All right, for this next one, we're working from this 47-degree angle over here. My opposite side is going to be diagonally across from it, so the opposite side is this one that's X. Hypotenuse is across from the right angle, so 9 is my hypotenuse. And again, I don't know anything about that adjacent side. So that means I know the hypotenuse. I'm trying to figure out the opposite, so that tells me again, we're going to be using sine. So the angle goes with the sine. So the sine of 47 is equal to the opposite side over the hypotenuse. This example is very similar to the last one. Right now, x is being divided by 9. If I want to get x by itself, I have to undo that division, and the opposite of division is multiplication. So if I multiply both sides by 9, that cancels out, and we have 9 times the sine of 47 equals x. So I'm going to go back to Desmos to figure out what 9 times the sine of 47 is. Again, sine is over here on the left. And it tells me that is equal to 6.58. So when I write it with one decimal, since the second number after the decimal is bigger than a 5, I'm going to round that up to 6.6. So my missing side length is 6.6. How cool is that? Trig is so fun. All right, last example we're going to do together. Starts out the exact same. From my 51-degree angle, my opposite side over here is 6. The hypotenuse is across from the right angle, and the adjacent side doesn't have anything written by it. So we know the opposite, we're trying to figure out the hypotenuse. Again, we're using sine. The angle measure goes with sine, so sine of 51 is my opposite side over the hypotenuse. When you get to a problem like this, where you have x in the denominator of the fraction, it's a little bit more steps, but the math is the same, so don't freak out. In this case, to undo this division, x is what is being divided by, so to cancel out the division by x, I need to multiply by x. So that's going to get rid of my fraction over here, and the left-hand side becomes x times the sine of 51 equals 6. Again, the sine of 51 is a decimal. If I plug it into the calculator, I can figure out what that decimal is. I'm just going to save that for the last step. So I haven't really gotten x by itself yet because right now it's being multiplied by the sine of 51. To undo multiplication, we use division. So I'm just going to divide both sides of the equation by the sine of 51. That's going to cancel out with that multiplication there, and x will be by itself. So x equals 6 over the sine of 51. To figure out what that's equal to, we're just going to go back to Desmos, clear out what was written in there before. So 6 divided by the sine of 51 gives me about 7.7. So there we go, that missing side is 7.7. And that is how to use the sine ratio to solve for missing side lengths on a right triangle. Thanks, guys.